to the Maui University of Hawaii Institute for Astronomy, the Pukalani Advanced Technology Research Center. I'm Dr. J.D. Armstrong. I put together these talks as part of my job as the Maui Technology Education and Outreach Specialist. I don't know what that means, so don't ask. I just cause trouble around here. We've had some really great talks, and I think that this is another good one. Dr. Emilio, I've known him for, what, about 14, 15 years. He's been coming to Hawaii every year to work with Jeff Kuhn on SOHO, and then SDO, and MDI, and let's see, HDMI data, mostly measuring the shape and radius of this and size of the solar limb. Today he's going to be talking about exoplanets, and so you might say that we have an alien talking about aliens. Okay, maybe I shouldn't go for the jokes. But anyway, let's give him a nice welcome to Dr. Emilio.
Just a second. Just put my pocket. Okay, can you hear me? Okay, good evening, everybody. Welcome. Thanks to him to my talk. When I wrote the abstract, we have more than 900 planets found. And on October 22, we reached the mark of 1,000 planets. Well, I've been very happy to that because I foresee that when I came to talk about that, we are going to have about 1,000. And yesterday I finished my talk and was very happy with that. And I wake up, have more than a dozen planets found. And I have to remake some of more slides, you know. I think we live in very exciting days because we are finding words each day, new words. You know, it's a very special time to astronomy. We are really living in an era of a revolution in astronomy. Did I turn it? Okay. Here what I plan to talk you about. A little of history about the first exoplanets. And I would like to tell you how we found those planets. How are the techniques, the methods to find new worlds. I will not describe all the 1,000 planets found, but I will talk about some of them, the most interesting ones, I believe. And at the end, I will talk about my own research, trying to find new planets. Well, the men always ask if it would exist another world. No? These two men, Giordano Bruno and Isaac Newton, they speculate about new planets as the Earth. You know, Giordano Bruno was died because that he was burned by the Inquisition. Okay, the first exoplanet found was Gamma Cephei AB. Okay, first I will explain the A. This is a double planet, okay, and the first planet we call A, and the second planet we call B. And we have another B letter here, that's B, that's lowercase. The lowercase means the planet, okay? the uppercase means the star, and the lower planet, the lower letter, the planet. But this one in 1988 was the only limit of our technology. And only some years later, this planet was confirmed. At the time, we really don't know if it was really an exoplanet or not. And this exoplanet around a pulsar is the first one that was confirmed on 1992. But you know, pulsar are a remain of in the explosion of a supernova, and probably this was formed after the explosion, you know. In 1999, really the first planet orbiting a star like our sun was found. Then you see that you can choose which one you can say that is the really first planet found.
What were the techniques used?
I will talk about describe the techniques, but those two are called Doppler measurements, and this one pulsar timing. It's a list of a technique. I will talk what Doppler velocity technique is. We'll talk a lot about that. Planet transit is a technique I'm using. I will talk a little about gravitational microlasing. I will not talk so much about the pulsar timing anymore. That's only 5 exoplanets found in this one, and really people question it's really a planet that, you know. Trans-time variation is a technique to find a second planet about a star. It's they see a variation on the time transit. It's like a perturbation of the first planet. Okay. I will mention astrometry technique, and we now can do direct imaging of planets. We can take pictures of the sky and really see the planet. I will show a picture. Okay, I will talk about Doppler velocity, and the first question for you: does a planet orbit around a star?
The center of mass.
Yeah, you can say maybe think yes, but really by definition the answer is not. And I will explain why. Okay, if you have any question anytime, just raise your hand. Okay. And why the answer is not? I have something called the center of mass. Okay, we can equilibrate objects in a point. Like if I can find a center of mass here, I can equilibrate. This is a toy. Okay. And you have a center of mass of 2 objects. Imagine 2 stars or 2 planets with the same size and same mass. Which one will orbit each other? Well, I'd say that they will orbit the center of mass. Okay, that's the equal distance between the 2 objects. Okay? When one of the stars here are bigger, in which direction the center of mass will move towards the biggest one? See? This is what I'm showing here. The center of mass now is inside the bigger star. And both stars continually, they orbitate in turn of the center of mass. But because the center of mass is inside the bigger star, the other stars looks to move very little. See? And how big is the star, more close to the center it will be. And the star will move less. And this also depends the distance of this body. If the second body is far, this motion here will be even fainter. Okay, then the question, is the moon orbiting around the Earth? No. Okay, the moon and the Earth are orbiting around a center of mass that is inside the Earth, very close to the center of Earth, but not exactly on the center. Okay, and this is a special case that we have in our solar system. This is Pluto. This is Charon, one of the moons of Pluto. And okay.
So, is there measurable perturbation in the Earth that results from the
Yes.
rotation around the center of mass?
Yes.
Does it have any effect, like on tide or anything that would be observable in the macro sense?
There is an acceleration caused by that. Probably is measurable. I would not see any measure, but I would say that probably we can measure that. Okay, between Charon and Charon and Pluto, the center of mass of the system is not inside Pluto; it's outside. Okay, Pluto make an orbit around the center of mass. Some people consider Pluto and Charon a double planet. Okay, then what is Doppler effect? So some of you who like this show Big Bang Theory, Sheldon one time went to this party, and his this fantasy was a Doppler effect, not a zebra. Okay, if you have a car, and the circles here represent the sound. Imagine that each sound was emitted after 1 second each other. And if the car is not moving, the circles are concentric, okay? On the second figure here, you can imagine the car moving. At the center of the first circle is when the car began to move, okay? Then let's think that he moved 1 second and you have the second one. But from that to that, the car moved. And the wavefronts in front of the car, they are closely and close. And those waves here are coming farther and farther each other, okay? Now you can imagine people around this movement. Okay, the guy in the direction of the movement will heard a high pitch. Okay, and the guy, this woman here, will hear a lower pitch. This is what we call it the Doppler effect, and it's caused by the relative motion. You can also thinking the car stop it, and someone moving around here. Okay, I prepare a sound. Let's see if it work. I think it's an ambulance. We can hear now the lower pitch, okay? And all waves suffer this effect. And the light is also a wave, but it's an electromagnetic wave. Then the light will not be lower or high pitch, but you became redder or bluer. If the objects are approaching us, they are bluer. So we said blue shift. and if the object is going farther, it's a blue shift. Oh, redshift. So sorry, redshift. Okay. I will not talk about that. For the you can imagine now the star and a planet around, and both are moving around the center of mass of the system. And we are not looking the planet because most of them we cannot imagine. We look at the stars, and we saw the star moving, the Doppler shift of that, or becoming bluer or red. Okay. This then is an indirect measurement of the planet. We infer to this happen, it must have a star a certain distance.
So you mean a star that has no planet wouldn't be moving?
Yes. Yes, or this planet can be very far and very small that we cannot detect, you know. Okay, then sometimes it's a blue shift, sometimes red shift. It depends if it's approaching us or is going another direction. Here?
Yes, so the spectrograph that you're showing is the light from the star that changes.
Yes.
Not the planet.
Not the planet.
Star.
Not the planet. Not the planet.
And are we talking about a shift that is nanometers, picometers, hundreds of nanometers? How much of an actual shift in
We can see the instruments now. The limit's about 1 meter.
Okay.
And 1 meter, I need to think how many angstroms will be. It will be
That's a
millimeters.
serious color shift that you're seeing.
Yeah.
If you're detecting only at a meter.
Well, it's small. We only have this, as I say in the beginning, we only have the technology to detect in the end of 80s, beginning of 90s, when we could build better instruments. The spectrograph that made these measurements is the size of a bus.
When you're asked a question, would you please repeat the question so other people can...
Okay, I will do that. I'm sorry. Okay. Most the other techniques, not, for example, direct imaging, needed to be validated by Doppler effect. Okay, like I will talk about the transit, but several things can cause this transit. And to confirm if it really is a planet, we needed to do this Doppler shift measurement. That's very difficult to do. Very small telescope on Earth have this capability. Then we have much more candidates to be planets than confirmed planets. Okay. Astrometry. Well, we can see the star moving in the sky. The very slow movement. We can only see this movement after several years with big instruments. And when we saw those data, we can see some perturbation of the movement. And also, the perturbation of the star is because the center of the orbiting around the center of mass. And we look at stars, saw the star moving a little, and we infer that there's a planet around. Okay, this is called gravitational microlasing. And this effect foreseen by Albert Einstein, that the light will be attracted by matter. For example, you have this source, and you have star here. This light here that would go straight would bend because the gravitational field, and this observer here would observe this source. Einstein foresaw that and tried to observe stars behind the sun during a total solar eclipse. Okay, and now people are trying to find out exoplanets using this technique. What happened here? You have you can think a fixed source, fixed object like a star, and this object passes in front of the source and us here. And what this does is to improve the light. We see an effect that's called this lensing. Okay, and this is the lensing effect. And here, besides, you can see another peak that was caused by a planet. And you can think here that this source have a planet this around, okay, and cause this variation on the light. Okay, these are real imaging of a planet. The star is covered by instrument called coronagraph. Because the star is too bright, we cover the light of the star, and we can see in infrared what is around. Okay, and those dots here are really planets around the star. Okay, planetary transit. Okay, I'm sorry.
So the determination at first, we're lucky enough to discover there's a star that's lensing.
Oh yes.
So now, and the measurement, the determination is because the movement of the star causes differences in the two lens images?
No. This is a direct effect because the.
Repeat the question.
Oh, I'm sorry. I need to repeat the question for the camera. You are asking if this is a direct effect because the movement of center of mass. No, this is different. Okay, this is because the mother star and the planet, they both suffer the same effect of lensing.
Okay. So is that able to detect a planet that's perpendicular to our point of view, as opposed to the transit where the planet?
Yes. Yes. Oh, the question is if we can find a planet that is perpendicular of Earth's sine of view. Yes, and the answer is yes.
So with lensing, we can find
Yes.
planets that are perpendicular.
Yes.
Very interesting. Thank you.
But we need to be lucky again to both
Right. And
pass in front of the massive stars, you know.
perfect.
Yeah, we need to have a perfect alignment. What these people, this is very lucky, but what the people do is observe all the sky at the same time. And some, with lucky, some of those thousands stars, one of them will have this effect. Okay, planetary transit. Here we need to be lucky again, because we need to be looking in the direction of the orbit of planet. We need to be lucky to see the planet cross the disk of the star. Okay, if you are looking like the pole of the plane orbit, we are not going to see nothing. And what happened here, that the planet, it block part of the star. It's like an eclipse. If this planet was big enough to cover all the sky, we will call that eclipse. But only he cover a small portion of the star, we call it transit. I will show an example. This is a Mercury transit in 2003, a scene from Soho, and this is Mercury. It took about 6 hours to cross all the sun. Okay, this is a planetary transit. And I have another one. This is also seen by Soho on 2006. 6 hours. Okay, and this is what I talk about. When the planet pass in front of the star, it blocks part of the light that comes to the star. And we see the light of the star drop. Okay, we call that the light curve. And we can measure the contact times when the planet enter and went out the star. The shape of this curve will vary, depends the star, what effect we call limit darkening, and even if the planet has some atmosphere or not. The shape can be very complicated. I have a simulator. Let's see if it will work. Oh, how I do that now? Oh, I'm sorry.
Can this only be done in space because of atmospheric interference?
No, that can be done. Oh, I'm sorry. The question is if this can be only seen from space, and the answer is not. Even if a folk telescope, JD have some students who saw some of a planetary transit right here in Halakala. Okay. Hope it works. Okay. This is a simulator. There's a website here if you can see. If not, I can give you at the end of the talk. Okay, and you can change the mass of the planet, the size, the distance, and you can see what expected from the light curve. You can see it changes. And I can maybe add noise to that, can I? No. Oh yeah, I can. Okay, if you have a good telescope, a big telescope, you see like that. But you have a small one, you're going to see a small effect. You know, it depends on noise. And also depends, okay, if you, I told you, you need to be lucky to pass in front. If you're very small angle change, it will not pass in front of the star, and you will not see the transit. Okay, when we observe a star, and we don't see a transit, that means that the star don't have a planet. Just means that we cannot see it. Okay, let's come back. Okay, questions? No? Okay, these are the techniques. I will talk about the planets now. We have 1,028 confirmed extrasolar planets. As far as today, I said yesterday was 1,010 yesterday on the website. And we found these 782 stars. Why there are less stars than planets? Because there are planets with more than one. Because there are stars with more than one planet around. Okay, we have 170 multiple planetary systems. Okay, here's some statistics that I told you that I had to update this morning after they found some more. Okay, here are here the number of extrasolar planets found, and you can notice how fast we have found planets. In probably 1 or 2 decades, we are going to have 1 million planets. I can come back and give you a million words. Mark?
But that 1,000 number is very conservative, right? There's actually been about 3,000 detections that are waiting for confirmation.
There are 3,000 from Kepler. I will talk about this unconfirmed, because there's remember, to confirm if it's a planet, we need to make this Doppler measurement. That's not easy to do, and it's very hard to have a telescope time to do. We have much more candidates today than confirmed planets. I will talk about Kepler candidates. Okay, here's the temperature of the mother star of those planets. And you can see that's about 5,000 Kelvin. To have an idea, the sun has 6,000, about 6,000. That's stars that are a little cooler than our sun. Okay, we don't have many stars in blue stars. We don't have many planets around the blue stars, around the hot stars. Someone know why? Can answer why? Based on what I told you? You remember that thing with center of mass, right? And if a star is too big, too massive, it will move very, very slow. And also, those stars, they have a very short life. They live on millions of years. Okay, that's not so much compared with our sun that will live billions. That maybe those stars don't have time enough to form planets around. That's the 2 reasons then. Okay, these are the age of the stars. So you can see you have a peak here around 2 billion years. Our sun has 5 billions. Okay, here's the orbital period. And we can imagine that it's much easier to find a planet that orbit around the star around some days instead 10, 11 years. Okay, we need to observe 11 years to see the complete transit. If you have stars that orbit in few days, it will be much easier to find. And okay, just one thing. All to say that we really have a bias when we look at those data, because we are always looking for the stars that are easier to find, not that most of stars have short periods.
Are different detection methods more common for finding ones in different things? If you've got a 5,000-year or 5,000-day orbital period, do the Doppler shifts not?
Yeah,
it just takes so long to observe that shift.
Okay, I need to repeat your question. If you have preference of some method to find the shorter or long period, okay, the answer is for direct imaging, for example, you don't matter the period you have, and also for the microlensing, what's important only it's passing in front of you. But for the methods that you need to see more than one period, like the Doppler shift or the transit, yes, because you need to be short, be easier to find. Those methods require that the star pass more than one time around the star. That will be much easier to find the planets with shortened years. Okay, here's some of the planetary systems that we already found out. It's called, oh, I'm sorry, I forgot to translate in Portuguese. It's 47 major bear. That's that? Ursa major. Big bear. Okay. I have two planets. They are okay. The first planet that is found out is B. The second one is C. Remember, here are the blue ones. Here in red are solar system in the same scale. And B have 2.4 times the mass of Jupiter, and C have 0.8 mass of Jupiter. Again, it's much easier to find a bigger planet than a small planet. Okay, it will be easier to find bigger planets around less massive stars that are close. They have the close planets, you know, have a short period. Those are the easiest ones. But we are really looking for is an extrasolar planet that looks like our own. We'll talk about that. This is Upsilon Andromeda, and this one have 3 planets, B, C, and D, and also comparable to the mass of Jupiter. See, the C is very close to the star. It's about, you have a planet about twice the mass of Jupiter around the orbit of Earth. Yes, here's the 876. We have 2 planets, and you can see that they are in the inner orbit of Mercury, how close they are. And they are comparable to Jupiter too. We call it that hot Jupiters, because they have a mass as Jupiter, and as they are very close to the stars, they are hot.
So I can see how mass could be estimated with gravitational lensing. How is mass estimated with the transit method?
Okay. He asked you how mass can be determined by transit, yeah, no, the period. And I would can remember the law of Kepler, that you have a relationship between the period of the planet and the called distance, but not the real distance. It's semi-major axis, but for simplifying, it's distance.
Period in addition to the
Stop.
reduction in luminosity.
It's not rotation, it's this translation period.
Yes.
Okay, and the relation between those, it depends on the mass. Okay, we use it up to today. Okay. Okay, this is another thing that I would like to talk about. It's called the habitable zone. When you are too close to the star, it's too hot, you find only water on gas, vapor. Okay. If you are too far from the star, it's too cold, you will find only water on ice. We know to have life, we need to have water on liquid state. Then there is a region that is not too close to the star, not too far, when we can find liquid water. This region we call habitable zone. That's the region that we are interested to find life. And the size and the distance of this zone, it will depend on the star. If you're too hot star, the zone will be more distance. And if the star is red, it's more red, it will be closer to the star. Okay. Then you are interested in the planets about the size of Earth, and they are inside the habitable zone. Those are the most interesting exoplanets to find. Okay, this is the ESA 667C. Why why C? Because there are 3 stars in the same system. Okay, it's a triple system. They have 3 stars. All 3 stars they translate around the center of the mass of the system. Okay, this is because C. This is the 3rd star. That's the fainter one. And around these stars, this C star of the system, we found 1, 2, 3, 4, 5, 6, 7 planets. That remember, all have 8. This is very interesting, no? This is why I'm talking about. And you know this B, H, C, F, A, D, and G. They are not in order because we put letters in order of discovery. Okay, and the H one was the last one we found out. And it's not a confirmed H. The 667CH is not a confirmed planet. We only suspect that this planet can exist, not still confirmed. But it's very interesting because here in green, it's the habitable zone of this star, and this planet is inside the habitable zone. I have 2 animations to show you. The first one is the movement of those planets, and the origin here is a hot zone, the end of the habitable zone near the star. Okay, and here in blue maybe it's too cold. Okay, and here's the real habitable zone, and I have maybe 3 planets inside the habitable zone of the star. They made an animation. How it looks like the vision from this planet. Okay, from this planet we could see 3 stars, like 3 sunsets. Okay, and you can see another planet here. You can remember a Star Wars movie when Luke Skywalker went out and saw 2 suns in the sky. This is not more fictional; it's real. We know that this exists.
In the animation with the orbits, why are the orbits generally circular, even though it's a tertiary star system?
Why the orbits are circular and not
Distorted by
okay.
the movement of other stars in the system.
Okay, because probably they are distorted, but we cannot measure with accuracy that. We can measure the orbit, but always have some margin of error of measurement.
The 2 stars, the 3 stars are very far apart.
Yeah, very far. This is why the system is. But they could say that the eccentricity is measured from some system, but not with very accuracy as we have in our solar system. You know that the orbit of the Earth is almost circular too. It diverges very little from a circle. Okay. Also again, we are interested in planets that have the size of our Earth and are inside the habitable zone. And here we have 3 zones. This is the hot zone, close to the star, habitable zone, and here is the cold zone. Okay, as I told you, most of the planets found are hot Jupiters. They're big planets, and they're close to the star. They are then in the hot zone. On blue are planets from our solar system. You have here Mercury, Venus, Earth, and Mars. And those on right here are the most probable planets that can support life because they are inside the habitable zone and they're up to 2.5 times the radius of Earth.
Well, I was just wondering, isn't it easier to find it when they're bigger and they're closer to the star?
Yes.
So that it's not really an accurate.
No, we haven't biased on this statistics because the big planets around the not so massive stars close, those are the easiest one to find. I need to repeat the question. Okay, the question is if those hot Jupiters are the easiest to find, and the answer is yes. Okay, here is what's called now the periodic table of exoplanets. As we have a periodic table of chemical components, we have now a periodic table for planets. This is what I try to explain to you. Okay, on the left here, we have the cold zone. Okay, the planets that are far from the star. The second line here are the warm zone. And here the hot zone, the planets that are close to the star. The columns means these are Mercurians, okay, planets as Mercury. Planets a little smaller than our Earth. Here are the Terrans, the planets as the size of Earth. The super Terrans, the planets that are a little bigger than Earth. The Neptunians and the Jovians, okay? Then the columns are the sides, and here the lines are the distance from the star. And as I said you, the easiest one are the ones that are in the hot zone, and the ones that are bigger. Those are the easiest one to find. This is why those numbers are big. And you can notice we have 0 here. We don't have any planet, confirmed planet, that are inside the habitable zone and exactly the same size of Earth. But we have about 10 planets inside the habitable zone that are twice bigger than our Earth. Okay? Okay, to compare, here's I was talking about is the periodic table of the exoplanet candidates from Kepler. Okay, probably all of them are planets. We don't know. We only don't have time, enough telescope time to observe 3,500 stars or planets. No. And again, we have a large number of large planets in the hot zone. Okay, to compare, I had the periodic table of our solar system. Okay, what planet are the Mercurian size that are in the hot zone in our solar system? Which planet? Mercury, yeah, of course. Which planets have a radius that is smaller than our Earth, that are close to the Sun? This one here. Mars. Okay, and this one is, of course, Earth. Okay, and we have 2 planets in the cold zone and size of Neptune, Uranus. Okay, and we have 2 other planets farther than the size of Jupiter, Saturn and Jupiter. Okay, that's clear now, the table. Yeah. I will come back here for you, give another look then for the found planets. Okay, we have some of the cold Jovians. Those ones to be detected that are farther need to be big. Do you agree? You are not going to find small planets as Mercury that are in cold zone yet.
Like the found planets, which you found,
Yeah.
not all the ones.
Okay. They have a list what is the current potential habitable exoplanets. And they put Earth and Mars here on scale to compare with those fine planets. Okay, the most probable one is called the Kepler 62e. That they are inside. Remember, it needs to be both inside the habitable zone and about the size of the Earth. But you can see that it's much bigger than Earth still. Okay, here's a diagram of Kepler 62. It's a star with a lower temperature, then the habitable zone is much closer to the star than the North Sun. Here's the Sun, it's Mercury, Venus, Earth, and Mars. Have 1, 2, 3, 4, 5 planets on this system. Okay. Here's the two main satellite experiments to find the planets. They all find planets using the technique of a transit when the star passes across the star. Well, unfortunately, none of them now are actually working anymore. They died. Okay, Corel have a problem on the CCD shutdown end of last year. It's about 1 year from now, and Kepler lost the gyroscope a few months ago. Well, I'm working on data with this satellite. It's called Corel. Was a project by European nations and Brazil. And we have access to the data. Okay.
Have they been successful in repurposing Kepler for near-Earth object detection?
I got an email, NASA. Okay, I need to repeat the question. If he is successful to use the Kepler to find out near objects, yeah. What I know, I got an email from NASA asking to submit proposals to what to do with Kepler, and this is probably one of the things that the people will do, because I think there's still 3 gyroscopes working and have some accuracy on the photometry, can do some things. I don't know if they already defined what they will do.
So it's still in discussion.
Maybe, I'm not will tell you, but I received this email some months ago. Maybe I don't pay attention about deadlines, but because I was not worried to submit nothing. Okay, I will not use some math, but I just would like to say that we use some math to do this stuff, you know. And those equations here is not to find the planet, in fact. It's just to correct the light curve. I will show some examples. The light curve is not so pretty. We have high energy protons that heat or CCD or camera. This change the light curve. They change the CCD, and you need to correct for it. Okay, this is the algorithm I'm using to find the planets. It's called box fitting square. What it means, we just fit a box here. We need to find difference between L, this level L, and H. That's deep of the transit. We need to know the size of the bottom of the transit, and we need to find this point here, P1 and P2, when the transit begins and ends. Okay, and this is described by this equation here. Okay, we try to fit a curve before the transit, this part here in red. This term here is after the transit, and the blue one is this part of the equation here, and we try to fit all together. Okay, we have many parameters to calculate. What we do, well, here's the real curve, here's the transit. Okay, we try to divide the curve in several pieces, put all together what we call phase diagram. Okay, and we are lucky enough to, not lucky because we are going to try several periods, several numbers until we reach one that is the correct one if this star has planet, you know. We found this one, we calculate all those numbers that I told you about, and we have a plot that a peak will appear when this happens. Okay, when we don't divide correctly here, we are going to have a small number, and when we have the correct number, we are going to have a peak on this, we call it spectrum. Okay, here's the red curve, it's the light curve with as an example, and you can see that something happened here. Yeah, this is when this proton came from the sun, hit the CCD, and this changed the electronics. Okay, this not coming from the stars, it came from the environment, from our sun. I need to correct for that. This is correction made, and this is the improvement of the correction we made. Okay, and those, you know, those are when the planet passed in front. Okay. Okay, this is another example. We corrected also for the changes in the bright of the star. You can imagine, for example, that this star have a solar spot or a star spot, you know, and this make the bright of the star change. We need to correct for that too. Here is another change in light curve. You can see here and here, and how we correct those jumps. One more example. Some of the spectrum, and we hope that those peaks represent a real exoplanet around those stars. Here simulate of some of the already found planets in the literature already published. Okay, and what we found, it's almost the same what the other people found. That means that our method it's working. Okay, we don't found the Grossa at B, that's very small, but most of the others we found with very high accuracy. Here are some candidates that no one found yet. We think that those stars have a planet. Okay, we soon will publish our relation of candidates, and for know if they are real planets or not, we need to ask time on the big telescope and do the Doppler measurement. Okay, and you can see how small it can be. Here on the red, it can be very small effect, because the planet or can be too small or too far from the star. Okay, I hope not speak so much. I finish. Thank you. Any questions?
How far away do you think is the nearest inhabitable planet?
Where? Yeah, because our solar system, well, it finished close to the Mars, very close to the Mars orbit. Mars was were inside the habitable zone. It's not anymore.
Okay.
Not the. Oh, I need to repeat the question.
Okay.
Where's
There's other planet that doesn't orbit our sun.
where's the nearest planet that's inside the habitable zone? That's not our sun.
Yes.
Okay.
That's inhabitable.
It's Kepler 62e that we're talking about. This great habitable. But you can see how big it is compared to the Earth. But you want to know in kilometers or in miles. I really don't know this number. I'm sorry, by head. But you can have this idea here. These are Sun, Mercury, Venus, Earth, Mars. Okay, and here is in blue the planet. You can compare with the Earth. You can see that it's much closer to the star than Earth.
But how far is it from us?
From us. And sorry, I don't have. Someone knows this number? Several light years. I have.
667?
It's Kepler 62. You don't know. We can check on the internet. Okay. 1,200 light years. 1,200 light years.
Yes, please, 667 is 22 light years.
Oh, these are close. But you know, they found the planet around Alpha Centauri that's only 4.2 light years. 4.2 light years. But this is a big one. No?
Question from upstairs. How many planets are around binary stars? Or
How many planets are around the binary stars or multiple system? I don't know this number, I'm sorry.
In the solar systems that contain 3 stars, like the one that you told us about, are those stars typically the same age, or what's the theory of solar system formation with multiple stars?
I don't know if you understand your question. You're asking if our sun is part of a binary or a multiple system, no?
No, you told us about the 3 stars in the same solar system. I'm wondering if those stars all formed at the same time, or if they're different ages.
Okay. We have a theory. Oh, I need to repeat the question. Good one. She wants to know if all planets are formed at the same time.
Or the stars in, like you told us about those 3 stars that orbit that same center of mass. I'm wondering if those stars formed generally at the same time, or if they're like very different in ages.
She wants to know if the stars also are formed at the same time to get to the planets, and the answer is yes. Okay, the theory that we have to stellar and planetary formation at those objects are formed from a cloud of gas. And I normally try to divide not all stars have the same life. I speak very softly. I would say we have 2 kinds of stars: the fat ones and the thin ones. And the fat ones, they live less than thin ones. But the fat stars, they shine much more. You know, they shine much more during the life, but have a short life. And when of these fat ones die, they explode in a form what we call supernova. And they spread all this gas around, and we call nebulosa. Remnant of a supernova is a nebulosa. And this nebulosa can form the second generation of stars. And just one nebulosa result from this fat star explosion can generate 1,000 stars. Okay, and all those stars have about the same age. Just one star, after it becomes a supernova and produces a remain of supernova nebulosa, this one can generate up to 1,000 stars. Yes. Nursery. I can show some nursery of stars on the internet. You can find. The second generation stars, yes, mainly the small ones, because we said at the beginning of the universe we have only hydrogen and helium. We have like carbon, iron on our body or Earth. This means that these elements came from a bigger star in the past. Okay, and after the star is formed, a material around the star will form the planets. Okay, this is the theory that we have now. Then the stars probably formed together as well the planets just after. It's very difficult to capture a planet. It can happen, no, but it's not very probable.
So from what you just said then, the theory is that the three stars in the tertiary system are the result of an earlier star going supernova and the resulting explosion condensing into three stars that now form that tertiary system.
Yes. Maybe you know cannot be secondary. You can have many generations of stars. We can never know how many stars came before.
But those three in that system continue to relate gravitationally to each other in a way that we can look at it and go, oh, there's a tertiary system.
Yes, because or else we not form. They don't have only hydrogen and helium. You have nebulosas that contain only hydrogen and helium. These are material from the Big Bang that formed in the beginning of the universe. If a star have other chemical elements, that means that they are second or third or fourth generation. It must have. Yes. The question is if those big planets are made of gas, and it's probably yes. No? Okay, one more. Okay, the question is if you have three stars orbiting the center of mass, if they produce more heat for themselves, for the planets. Well, the heat will depend on basically the mass of the star. The temperature of the star will depend on the mass. How much heat it will produce, it will depend on the distance. You can think, well, we got the heat from all the stars in the sky. That's true, but very small amount.
So these three stars are the center of the galaxy, right? The center of that particular galaxy. Not galaxy, solar system.
The center of solar system. Remember, the center of any. The question was if those stars are the center of the solar system. Remember, the center of solar system is the center of mass of the system. It's not in this particular case, not inside that particular star. There's nothing on the center, just a mathematical point. That's the center of mass.
But the three stars are in the center of a solar system, right?
If the star of the system, no, that we'll come back. Okay, I don't. Oh, why?
It's on.
It's on? Okay, the center of the planetary system is this point here, the center of mass. The stars are not in the center. You know, you have in this case you have a third stars that are more complicated situation, and those planets are orbiting those stars at the same time. They made a very complicated movement in terms of center of mass of planets, but the stars are not in the center. Around the star, yeah. You have situations that is possible. For example, is a planet orbiting both stars at the same time. Yeah, this is possible too. But it's not the case that I show you. Those planets are orbiting a particular star.
So if for some reason, as you show, the stars actually come closer together,
Mm-hmm.
and then they go further out.
Yes.
That would create more heat on the planets, right?
Yes, in the sense that you receive more light from one of the stars, yes. Okay. But remember, the distance we are talking they are very far from each other. Is that okay? More questions? No, that's all. Okay, I appreciate you coming tonight. Have a good evening.